I will be explaining slowly. If you have uncertainties on the explanation given, please just let me know so that we can move together. So the first question says, like I indicated, this is 2018, 2018, paper 2. This is internal. So the question says, which of the following sublimes when strongly heated? So we understand the meaning of sublimation. This is a physical change, changes of state that we know from a solid direct to a gas, but without passing through the liquid. But there are some substances that do not go direct. They have to pass through the liquid state. Now here, among the ones that we have, the only substance that sublimes is iodine crystals. So iodine crystals is the answer. Which of the following? So we have these items. You just choose the one that sublimes when strongly heated. And this is iodine crystals. The second one is saying, we're saying the answer is yeah. The second one says, identify the measuring apparatus shown in the diagram below. So this measuring apparatus that we have, we can see the mark. This mark here indicates the fact that this measuring apparatus can only measure a fixed volume up to the mark. There is only one mark indicated. And this is what we use most of the times for standardization of solutions. And this apparatus is called the volumetric flask. This is the volumetric flask. A conical flask is what we use for conical flask for titration. Then the density bottle, we use it for measuring the density. The separating funnel is used for separating immiscible liquids. So the one that we have is a volumetric flask that we use most of the times for standardization of solutions. Question number 3 says, what term is given to atoms of the same element? So the key thing here, talking about atoms of the same element, they have the same atomic number, but the only thing that is different are the mass numbers. So isobars, mostly this is talked about in isobar is mostly talked about in geography. They were told that these are lines that joins areas with the same pressure. Bar is to do with the pressure. And then the isomers, these are compounds that have the same molecular formula, but their structure formulae are all different. Then the isoelectronic, we're talking about having the same number of electrons in an electronic structure. same number of electrons in an electronic structure, but this one is talking about same number of atoms, and therefore the answer is an isotope. So most of the times when we hear the word iso, we are told that there must be something that must be equal. So the first one, what is equal, is the number of electrons in an electronic structure. Isomers, we're talking about the structure, the molecular the molecular formulae are the same. Isobars, the same pressure. So the one talking about the same number of the same element with the same number of protons. That's the atomic number we're talking about. So the atomic number here is the number of protons, not number of electrons, as in per se, because we also have same chemical species that have the same number of electrons, especially when one is an ion, the other one is an atom, we are likely to have such possibilities. Like let's say lithium, Li73. So when it is lithium ion, meaning instead of having 2,1 configuration, this one is lost. Therefore, the electron configuration of lithium plus lithium ion is just 2, which is the same as helium 4, 2. So these may be called the isoelectric because the number of electrons are the same, but the number of protons in these two will be different. Therefore, they cannot be called isotopes because these atoms are different. So here is isotope. Question F. We're talking about metallic bonding. We understand the three types of bonding. There's ionic, metal, non-metal, covalent among non-metals, but metallic bonding, we're talking about just the force of attraction that is there between the valence electrons as well as the metal ions. So the loss and gain of electrons, this is ionic. The electrostatic between all protons, this is not true. Mostly the electrostatic forces between the protons and the electrons, no, unless among protons themselves within the nucleus. That's why we talk about the binding energy, the mass defect, and the like. The sharing of electrons among nonmetals, this is covalent. So the force of attraction between the valence electrons as well as the metal ions in the metal lattice, that is what we are calling as metallic bonding. Our F5. Which of the following oxides can be neutralized? So we're talking about oxides that can be neutralized by both aqueous sodium hydroxide, this is a base, as well as the sulfuric acid, this is an oxide. So we're talking about an oxide that can react with both the acid as well as the base. And these type of oxides are called amphoteric oxides. So among the examples of the amphoteric oxides that we can talk about, you can talk about Pb oxide, which is lead oxide. We can talk about aluminium oxide. We can also talk about zinc oxide. Now, because among these three that we have which belong to the amphoteric oxide, the only one which is here is plumbium oxide. Therefore, this is a practical example of an amphoteric oxide that can react with both the acid as well as the base. Okay. Then the other one that we can talk about is next set of questions, which is S6. Now, because S6 is a little bit big, allow me to have a single question on the page. So here, we are taught to start the reaction scheme. Most times when you hear of the reaction scheme, it means there are some interconnection of reactions. Okay, and mostly this is common in organic chemistry. University organic chemistry, that's where we're going to have a lot of interconnected reaction schemes. So we are told that we have a black solid. And in most cases, the black solids that we have, among them, the common one is anhydrous copper oxide. Copper oxide, which is anhydrous without water of crystallization, we expect this to be black. So it is a copper oxide which reacted with dilute sulfuric acid. So this reacted with H2O, H2SO4. So this, okay, maybe allow me to write them here. We have copper oxide, which did react with sulfuric acid. Let's see the products that we're going to have. Sulfuric acid, and this is a double displacement where the entire copper comes to take the place where hydrogen is, thereby forming copper sulfate. So this copper sulfate that we have here is copper 2 sulfate. And most of the times the two ions, the copper 2 ions, mostly when they are hydrated, meaning water must be present. So we have got the H2, which is here. We're going to have the H2 here being formed as a byproduct, plus the oxygen, which was on the oxide. This is what we're going to have. So because of the presence of the water in that reaction system, and then we are also going to have copper 2 ions. That's why we have got the light blue color. So this light blue color is coming from the copper 2 ions that are present in the solution. So this light blue solution here in B, it is copper 2 sulfate. So this is what we have on B, this is what we have on A, and this is what we have formed as a solution C. The other thing that we have to know is that why are they saying a solution? It is because if we are to supply the state symbols, the copper 2 sulfate is a very soluble salt. That's why we are saying it is a solution. If it was an insoluble salt, we could have used the word such as a PPT, a precipitate of a salt that is formed. So A, it's copper 2, it's copper 2 oxide, it's copper 2 oxide. So we can settle for A, we can also settle for B, depends on the outcome that we have on the other side. Then the liquid C, we can see that it is water. Therefore, A qualifies to be the answer. Now, supposedly, we were told to extend the reaction scheme all the way up to finding D. So what reacted is this B. When this copper 2 sulfate reacted now with, that's why I said the reaction scheme is some interconnected reactions of chemical species. So if it was this copper 2 sulfate, which reacted with the sodium hydroxide, followed by excess of it. So meaning excess of it, they want to make sure that the other chemical species finishes within the chemical reaction. So if we if we're asked to extend our knowledge all the way up to D, insoluble in excess of D, what we are likely to have is a copper 2 sulfate reacting with sodium hydroxide. So when sodium hydroxide reacts with copper 2 sulfate, even here is a double displacement. Copper takes the place where sodium is, but understanding very well that copper has a valence of 2, so we'll have copper 2, and then hydroxide has a valence of 1, so we'll definitely get that. That is copper 2 hydroxide, and then plus sodium here, and then a sulfate, we get to have sodium sulfate. So this is how far we could have gone on the other side of the reaction. But because we're just told to end on solution on liquid C, therefore we settle for A as our answer. We go to questions A7 as well as A8. So A7 says, we are given the pure sample of zinc. Why did they say pure? If the word pure was not used here, it was going to be very difficult for us to solve this question. Why? Because if the sample we're given is not pure, then we cannot use this mass to find the number of moles of zinc. Because we will say that part of the mass that we're given was for the other impurities which was combined in zinc. But it has to be pure, so that when we are to account for the number of moles, we are going to use the exact mass because the entire mass was for zinc. So this zinc metal reacted with the volume of this HCl acid was 100 mil, but remember the volume, the units are not decentimeter cubed, but supposed to be decimeter cubed. And the concentration was 2.0. So the question is, which one of these two substances was a limiting reagent? If one is a limiting reagent, then the other one must be in excess. And then we are also told to foretell the product. So the number of moles for zinc, we will say that zinc, the number of moles will be equal to the mass. So it's always important to start with a formula, the mass over molar mass. So the mass that we are given for pure, it's 7.8 grams. Then we divide by, if we check the periodic table, zinc has the molar mass of the mass number of 75. And when we divide these two, we are finding the answer to be 0.12 moles. So these are the number of moles that zinc has in the solution. What about HCl? So HCl, we're going to use the formula conc is equal to moles over volume. And therefore, the volume we must multiply. So volume must be equal to the moles multiplied by the concentration. Provided the number of moles are given, then the concentration, provided, I think I've switched. I have definitely switched them. Yeah, this is volume, so it's this one that I'm supposed to take out. So it has to be the number of moles. The number of moles is equal to volume in cubic decimeter multiplied by the conc. But if we look at the volume that we have, it's 100. So this 100 must be divided by 1,000. That's our conversion factor. And this will give us 0.1. So the volume here was 0.1, which is multiplying, this is 0.1 is multiplying our concentration is 2.0. And when we do that, our number of moles is 0.2 moles. So we understand very well that the moles that are in short supply represents the limiting reagent. And the moles that were in excess supply presents the chemical species which was in excess. Meaning these moles are a lot, they will remain when the reaction is done because this one will have completed while we still have about 0.8 remaining for the other chemical species. So therefore, the limiting reagent was zinc. The one in excess was HCl, was HCl. But the question is what will be the products? The product is this. So we'll say Zn plus HCl, HCl. We'll not even balance it. The balancing is what is actually going to guide us. So we are forming Z. Now remember, zinc is the only transition metal that has a fixed valence, and the valence is 2. That's why we are seeing the presence of these 2 here. Now, because there is no 2 here on ZL, on Cl, therefore this is the wrong one. Not only that, hydrogen is a diatomic element. So there must be the diatomic existence of hydrogen, which in our case is there. So the only thing that causes C not to be the correct answer is the omission of a 2 on the chloride. Am I too fast, guys?
No.
Okay.
No.
No.
We can move on. Okay, we can move on. Cholwe, are you back in Zambia?
Yes.
Oh, I see. Okay, so we move on to A9. Now, be reminded that when this first session is done, the second session that we're going to have will be for math. So we have A9. A9 is coming from the topic that we just started, though we haven't done far. This is called chemical reactions. So the question says, a learner carried out an experiment on the rate of chemical reactions. The results of the experiments were recorded on the graph as shown below. So this is what was recorded. If we take a particular point here, time t, at this point, let us see how the reaction was. If we are to extend it up here, you will find that within the same amount of t, the volume that was produced, because we're talking about the volume of the product, for reaction 1 is here. For reaction number 2, this reaction number 2, the amount of volume which was produced is here. For reaction number 3, the amount of volume that was produced is here. And for reaction number 4, this is what was produced within the same amount of time. And we can see from the graph that the volume increases as you go up. So what information can we get from here? Is that reaction 1 produced less amount of product in terms of volume. Reaction 4 produced the maximum amount of product within the same amount of time. And what do we say about the reaction which is very fast? The reaction which is very fast is the one which is producing more of the product within less amount of time. If we are given a platform to have eating competition, Then they tell us to start. Then they say we'll be recording how much of the food you eat per minute. If we get to have one person who has eaten almost the entire food within 2 minutes, while others are still having a lot of food on their plate, then you will say that the one who has eaten more food within a short period of time is the one who is very fast. So as a result, we will say that the reaction which is the fastest is reaction number 4. Why are we saying that? It is because this reaction actually came to an end at this point. Then the reaction number 4 came to an end at this point. This is the time when the reaction number 4 came to an end. Reaction number 3 came to an end at this point. Reaction number 2 came to an end at this point. And reaction number 1 took the longest. So the one which was very slow is reaction 1. Reaction number 4 was very fast because the reaction came to an end earlier than any reaction that we have. If we are to move on, question number 10. Question number 10 says, element W has high melting point, high boiling point. So just these two, we expect this to be a metal, because metals are the ones that have got high melting point and high boiling point. But we have metals in group 1, we have metals in group 2, we have metals in group 3, we also have metals that are called transition metals. But of them all, the ones that have the highest melting point are transition metals. But we cannot guess from that. Let's go on. We are told that element W can form an oxide, 2 oxides actually. The first oxide is WO, meaning the valence here was 2. The same element W can form another oxide with the valence of 3. So this valence of 3 is what is the valence for this number written here is the valence for W. And because here nothing was written, it's because oxygen also has a valence of 2. So these valences cancel them out. So because the balances are different for the different oxides it can form, the only element that have multiple valences are transition metals. So transition metals are the ones that have multiple valences. Question 11. Rubidium is in group 1. When we say group 1, we mean 1 electron in the outermost shell. Now, which element is in the same group, meaning group 1 with rubidium, but is found in, which element is in the same period, meaning with the same number of shells, same number of shells with rubidium, and yet it is found in group 4. So here, the best that we can do is just to rush down to the periodic table. When we find the periodic table, I will just ask you, I think we have gone further. I will just ask you to twist the phone a little bit so that you can see the periodic table. So this is what we have. Unfortunately, Apple, I don't know how to rotate the document. I don't know the shortcuts. So we can just turn the phone or whatever gadget you are using a little bit so that you see what I'm talking about. So this is what we have. We are told that this element is in the same period as rubidium. So this is our rubidium here. This is our rubidium. And because they're saying this element is in the same period, so one thing that we know in mind is that it should be found within this period, because this is a period in which rubidium is. What else are we told? That it's in group 4. So this is group 1, this is group 1, this is group 2, this is group 3, and this is group 4. So we also expect this element to be in group 4. So where the group goes downward. So where these lines are intersecting, that's where we have the representation of the element that we are talking about. Same group as rubidium, and it is in group 4. And this is called tin. So tin is the answer to the question that we are from talking about. So the answer here is SN, which is tin. Okay, but I don't know how I jumped question A8. I'll come back to it. Let me just finish this page. So question A12, metals are able to conduct electricity. Why? We were talking about metallic bonding, that metallic bonding is a force of attraction between the mobile electrons as well as the metal ion. So why is it that? It's because these electrons that are found in metals are very much delocalized. So these electrons are very much mobile. That's why they are even able to conduct electricity. So metals conduct electricity because the electrons are delocalized. Now, how do you explain the delocalization of electrons? Let's take a shell. This is our shell. And this shell, we understand that metals have electrons that are in the outermost shell, 1, 2, and 3. So we're going to take 2 examples, this first shell and this shell. For non-metals, the number of electrons are 5, 6, as well as 7, even 8 noble gases. So let's take this scenario that we have and let us see. For non-metals, we are going to put these electrons, in the shells. There are only 3, 1, 2, 3. But for non-metals, let's pick the one that has got 7. 1, 2, 3, 4, 5, 6, 7. Now, meaning for non-metals, there is only one space which is left for an electron. So meaning the mobility of this electron is just within this range. Because here there are electrons and here there are electrons. So this is the only movement that it has. But look at this electron. This electron can move all the way up to that, can also move all the way up to that. So that is the mobility we are talking about. They are not localized. Delocalized meaning they are able to move about, and this is only possible in metals. So this is a simple explanation that we can give. Then question 8. How many moles of oxygen can you occupy the volume of 1200 cubic centimeter at room temperature and pressure? How do you answer this question? You come here. There is a very important information at the very end of the periodic table. This information talks about the molar volume. So it is saying that the 1 mole of any gas, occupies the volume of 24 cubic dense meter. Any gas. Oxygen is not an exception. So we have oxygen here. How many moles? So first of all, they're saying 24 cubic dense meter. So let's convert this to dense meter by dividing by 1,000. And when you divide by 1,000, we are going to have 1.2 cubic decimeter. So this is the volume that is there. And it's just a simple proportion that 1 mole gives us 24 cubic decimeter of the volume. So we don't know how many moles that will occupy the 1.2. So when we cross multiply, we're going to have 24x is equal to 12. and 1.2. And when we divide by 24 here, we also divide by 24 here. You can do the division here. We are saying that 24. Allow me to perform here. We are saying 1.2 divided by 24. The answer is 1.2 rather. 1.2 divided by 24. So the answer is 0.05. So when we go back to our document, you'll find that the answer is 0.05 moles. The last one is 13. We understand very well that metals, especially iron, is meant to rust. Now, there are three conditions that must be present there for iron to rust. The first one is moisture. There must be moisture. There must be the iron which is rusting. There must also be oxygen. So, in a test